Good morning, class. You're welcome back to my channel. My name is Miss Sandra. So today we'll be doing a revision class for 200 level mid-semester exam that will be coming up. I'm going to be running through with you guys and everything that we've done. Our exam is coming up on Thursday, so let's just get prepared. This is a makeup class for anyone that was not able to attend the class. I'm going to be a bit strict while marking, so if you know you've not attended the class, make sure you watch this video to come on board with everything I've taught. So I'll be running through with you guys on gram staining and immersion of bacteria. And I'll be doing another slide on the colony morphology microorganisms later to run through with you guys. But for the mid semester, I'll be focusing on the gram staining and immersion of bacteria. So stay tuned and welcome to class. Gram staining. Let's start with gram staining. So you can still go back to my former video on gram staining and watch it. But let's just do a little revision on this. Of course, for the next semester, for the exam, you need to be aware of why you stain gram, why we stain microorganisms. Why do we stain microorganisms? We stain microorganisms to be able to differentiate them to have a contrast between what you're seeing on your plate and the environment. Imagine if you did not add a stain to your microscopic slide and you're trying to view to the microscope, it will be so difficult to differentiate the presence of your organism on your slide than presence of your organism on that slide when you're looking at it without a stain. So staining helps us to be able to identify the organism on the slide and be able to even know what you're looking at, see some important things on the cell of the organism that will help you. I say this is E. coli, this is Staphylococcus. But that's basically why we do gram staining. So we have basically two main types of staining techniques: differential stain and the simple stain. In the simple stain, we usually use one simple stain, one stain. Then for the differential stain, we make use of different stains, mirrors. For example, the gram stain that I'll be talking about, we make use of two stains here. So, of course, that gram staining was discovered by Christian Graham in 1882. We're not going to be talking about that detail because we're not historians. We're going straight to what is the principle of gram staining. The principle of gram staining basically works on the idea that some groups of microorganisms can be differentiated into gram-positive and gram-negative organisms based on the presence of the peptidoglycan that is in their cell wall. For example, the gram-positive bacteria, which popular ones are Staphylococcus aureus. Make sure you're aware of the examples. These organisms have thick peptidoglycan layer in their cell wall. While for the gram-negative organisms, they have 10 glycan layer in their cell wall. So yes, the presence of this peptidoglycan layer is what we use to differentiate this organism during gram staining. And for gram staining, we have 4 basic steps. You don't need to be, some people were asking me in the other video, the steps are 5, the steps are 4. I'm not even sure of the step. All I know is give me the details of the step and don't miss anyone. I think it's 4 or 5, but once you're in track, you know you're in track. So how do we do the gram staining? Of course, you're going to be taking a loop from your petri dish that you've already grown your sample overnight or whenever you grew it, and you'll be inoculating it on your plates. Then after that, the first thing we're going to be adding is the crystal violets. First, you're going to fix your sample by making a smear on your slide. I've talked about this in class, but if you're not in class, make sure you listen carefully. After you've heat fixed and you've made a smear, you're going to be adding the crystal violets, which is the first thing we use in gram staining. After the addition of the crystal violet, what are we going to do next? We're going to wash it off. You leave it for a few minutes, then you wash off. After you washed off, what are we going to add next? We're going to be adding something we call Lugos iodine that would help, which acts as a mordant to help it stain, help the cell of whatever bacteria that is present to retain the stain. So we're adding the Lugos iodine. After the addition of the Lugos iodine, what are we going to do? Then we go back to the very critical step in gram staining, which is the decolorization. We're going to add in a decolorization. Why is this step important? It's very, very important. If you miss this step, you won't even be able to identify any stain. It will clear off all the stains you've used. So it's a very critical step in gram staining. Addition of of the colorizer, which is alcohol. If you leave the alcohol present on your slide for a long time, it might clear off all stain and you will not be able to identify any color when you view, and this you lose the purpose of doing your gram staining, and it can even damage the sauce. So this is a very critical stage in gram staining. So we're going to add in the crystal the colorizer, the alcohol, to know if it will take off the stain from the take off the crystal violet stain from the sample. Alcohol. Okay, so after the addition of the alcohol, you leave it for a few seconds. Me, I told you the rule of thumb is to leave for a few minutes, but me, I just count. I just breathe and I wash off because I don't want to have problem. So after you've added your crystal, after you've added your alcohol, the next thing you're going to be adding, you wash off, then you'll be adding your second stain, which is what? The saffron. And what color is this? It's usually purple or dark blue. And you add your saffron in, which is red. Please note that after you've added this, you still wash it and you view a microscopic slide. So for a gram-positive organism, we'll still be having the purple color, and for a gram-negative organism, it will become the red color. Why is this? A gram-positive organism has its peptidoglycan. So even when you've added the alcohol, which is a decolorizer, it will not wash out the stain. But for a gram-negative organism that has its same peptidoglycan, once you add the decolorizer, it's going to wash out the crystal violet, leaving behind only the saffron, which is the secondary or which is the counter stain you'd add later, and it will be retained. So when you view on your microscope, you have to be having something at the back of your mind. And once I see purple, I know that this sample is a gram-positive organism. And when I see red, I know that this is a gram-negative organism. Make sure, do well to have examples of these organisms off heart. For gram-negative organisms, you know that Klebsiella is one of them. For gram-negative, Klebsiella. Gram-positive, I'm just seeing one off of my head, we have star. I give you so many examples on my slides, so do well to read them all. So this is basically what happens in gram staining. So make sure you take notes of every other thing I give you guys on the slide. I'm focusing on the major things you're meant to be aware of. So let's go straight to the second one. I'm also looking at my slides so I don't miss any. I'm going to enumeration of bacteria right now. One moment. Okay, so back here I'm in my slide, the enumeration of bacteria. I just want to run through the revision class. Okay, so enumeration of bacteria, what do we need to know? What is bacteria enumeration? Enumeration of bacteria is to determine the number of organisms, just like human beings. What do we call the enumeration of human beings? Carrying out census. So it's just like carrying out census for bacteria. For any sample you're working with, mostly in food industries and health, they need to know the number of microorganisms present in a sample. Just like when Nigeria wants to know the amount of human beings they have in Nigeria, that they can distribute their resources. We also need to know the amount of microorganisms that are present in some of the samples we consume, that will know if it will have any negative effects on the consumer, the person taking the sample, like your food, your drinks. It's very critical in food microbiology and industrial microbiology. Okay, so let's go to the methods we have. Okay, the first method we have from my slide, and as I told you guys in class, is direct cell count. This is where you just view directly under the microscope. You can just go to the slide and go through it. Then I want to go straight to the using fluorescent dye. I told you guys that with direct cell count, you can use fluorescent dye to help, or you can magnify the presence of the organism you're looking at. And you can see from my slide, this is just a microscopic view of what we're talking about. Direct cell cell count. Make sure you know you're going to use an immersion oil for this viewing. It has advantages and disadvantages. Do well to know the importance, the advantages and limitations for each of the methods you're talking about. So we have the standard or viable plate count, which is the one we focused on. This is when we carry out a pour plate method and we allow the colonies to go. Then we carry out our colony forming unit. We count. I told you guys that in class, in microbiology, we have the total number of what we accept as our count, which is 30 to 300. This is the accepted value. So how do you do your coloniforming unit? I know some of you were confused in class. Let me just go through it again. Of course, you're going to carry out for serial dilution, because if you use the original sample, like you went to market, you bought vegetables and you're trying to find out the amount of vegetables, microorganisms in that vegetable, it's going to be so too numerous to count. So we have to dilute out this sample into a series of nine test tubes. So what we call the first water you've added to your vegetable and you've collected it, the stock culture. From that stock culture, you take 1 ml, and before ahead, you'd have pipeted 9 ml into nine test tubes. Then from your stock culture, you take 1 ml and you start the dilution. You dilute into the first test tube, and that is 10 raised to power 1. You dilute into the second one, 10 raised to power 2. That way to the ninth one. Then now, how do you achieve your plate? You look at the sample. Looking at your stock culture, if it looks so dirty, you might be taking your sample, the one you put out on your agar. You've already prepared your media in the lab. You've set out your plate and you've allowed it to set. Like it has. When you pour your plate, it's going to be in liquid form. When you leave it for a few hours, it will gellify and it will form a gel. So you are now about to pour like 1 ml into that gel and allow it to grow. So you might choose your sample from the 5th test tube, that's 10 raised to power 5, 6th test tube, depending on your choice. So once you've determined what test tube you want to use, then you take 1 ml from that test tube and pour all on top of the agar gel you've already prepared, and you let it to set. When you come back tomorrow, you're going to see a lot of growth. Looking at the plate, we use something called colony counter to count. You count your petri dish for a number that has 30 to 300. Now, how do you determine the coloniforming unit? I gave you guys a formula for it. So after carrying out this processing, that the coloniforming unit can be determined. So this is all that I was talking about. So we're going to determine our coloniforming unit by the number of, if you have like 270, which is still in the range, times your dilution factor, 270 times 10 raised to power 6. And it's going to give you your total number of cells, which is number of organisms present. I told you guys in class. So whatever value you get times the dilution factor you used, and that is your answer. So if you're having 270, to be 270 times, if you use 10 raised to power minus 6, 270 times 10 raised to power minus 6, which is going to give you, let me say, I don't know the value, calculate it, CFU per ml. That's the answer. That's how we calculate it. Okay, so let's go down again. What other? Make sure to know the advantages and disadvantages. Of course, this method takes time. That's the only most of disadvantage. And sometimes you have a lot of colonies to count. It's time consuming. Unlike direct cell count, which is very easy to do. So this is the limitation. This is the advantage. Make sure you know the advantages and disadvantages. And let's talk about the turbimetric method. I told you guys that turbidity, of course, is when something looks cloudy. You can't see through it. You say the water is turbid, you can't see through it. So now when for example, let's go back to the vegetable you got from the market, and you've poured water and you're seeing a very dirty water sample. Now how do you calculate? You don't want to use the colony viable. So now you know the method: direct cell count, viable, standard or viable plate count, and now turbidometric method. So now you don't want to use direct cell count, you don't want to use the viable method, viable colony counting method. Now you want to use turbidometric method. You're going to be passing the turbidometer through the turbid tube you have containing your stock culture. The passage of light is what this instrument measures for you. Do you understand? That's what really happens in turbid. As you can see here, this is direct light. You can see that this test tube is not turbid, and all the rays of light passed, and to measure it. But unlike this one, this test tube is turbid, and you can see it's only one ray of light that is passing through. So this is how we measure it. The advantages of turbidometric method, of course, is very fast. Disadvantages: requires a high amount of cell organisms. Yes, your water needs to be turbid for you to use this method. Imagine if you did a dilution and your water is clear. Of course, there will still be bacteria present, but you cannot use the turbidometric method for it. If the mass of bacteria increases more than normal in the sample, then they max the light pass. Yes, if you have so much amounts of bacteria, nothing will pass through. So what do you calculate? This is one of the limitations. Okay. So that's basically everything we need to know for the mid-semester. Make sure you read through the slides very well. And see you guys on Thursday for my class. Thank you and bye. Of course, I'll be waiting for you guys to drop your questions, and I'll be ready to answer your questions ahead of the mid-semester. Make sure you drop your questions before Thursday. Thursday is our exam. See you in the exam hall. And good luck to all of you. Bye.